Properties of waves. We're studying the electron, and we know that electrons are so small that they behave between energy and matter. This means that electrons have wave-like properties. Therefore, they're not quite things. They are not subject to the normal behavior of matter, and so you're going to end up with some rather unusual consequences. Since they behave like waves, it's a good idea to understand waves. Waves have a wavelength, which would be the length of that wave, which would be from crest to crest, or, if you prefer, from trough to trough. The amplitude would be basically half the height of the wave. It would be from this point here to that point there. Only rarely does this show up in any sort of chemical calculations, whereas wavelength, frequency, and the speed of light are the typical calculations that a chemist might have to encounter when determining properties of electrons. The frequency, it's a good idea to become comfortable with that. It means how often. So remember that this wavy line here is moving at the speed of light, and so it will pass by a fixed point extremely frequency, since the speed of a wave is 300 million meters per second. So even for a wave the size of a football field, you'll be dealing with a frequency of greater than 10 to the 10th times per second, a very high number. So it's defined basically as how often, or technically the number of waves that passes through a particular point in 1 second. They call it a cycle per second. That's more of a physics term. It's rarely used in chemistry. In 1873, it was proposed that visible light consists of electromagnetic waves. This is no doubt related to Young's double slit experiment, and it was referred to at that point as a wavy disturbance of energy. If you look at it a little closer than we really need to, from a chemical point of view, it has not only an electric field component, but also a magnetic field component. The speed of light, as we've said before, in a vacuum is extremely fast, and all electromagnetic radiation satisfies the speed of light equation, where the speed of light c is equal to the wavelength lambda times its frequency, where frequency is how often. There's 3 possible units for frequency that all mean the same thing: hertz, hc, or 1 over seconds, which is the same thing as seconds to the minus 1. The frequency is always inversely proportional to the wavelength. As one goes up, the other one goes down. And let's go ahead and perform a calculation. If you want a little practice, take out your calculator now and go ahead and try this by pausing this before I give away the answer. Here's the question. The wavelength of green light in this particular situation, it's a traffic signal. Let's say that it's centered at 522 nanometers. Let's determine the frequency of this radiation. Start with the speed of light equation and off you go. Okay, to solve this you just have to rearrange for frequency. So if the speed of light equals wavelength times frequency, frequency equals the speed of light divided by the wavelength. And if you go ahead and do this, you'll be fine unless you forget to use like units. Most common error is people type in 522 nanometers, hope that it works, and in fact it should be like units. So we have not 522 meters, but 522 billionths of a meter. That should be a superscript right there. Solving this should give us, if I can get it, there it is, over 10 to the 14th hertz for that particular wavelength of light. Notice how large these frequencies tend to be due to the incredibly high speed of light. Let's take a quick look at the electromagnetic spectrum. Here we have the very small wavelengths, less than a thousandth of a nanometer, for example. I believe that would be 10 to the minus 12th meters, up to 10 to the 13th meters, a very, very large wave, extremely large wave. The frequency you'll notice is inverse to that. Here's a very large number, here's a much smaller number. Here, the ones that are dangerous are the ones that are more frequent than violet. So visible is right there, and it should be Roy G. Biv. How do I know to put it going from right to left here? Because I always remember that Roy is for red, and next to red is infrared. V is for violet, and to the left in this case of violet is ultraviolet. So this is the scary region. This is the safe region. Next to violet is ultraviolet. Next to red is infrared. They're all so high because light is so darn fast. And here's your dangerous waves. Here's your safe waves used for communication, etc. And here's the tiny little region that we can see from red to violet.